Let us take a look at an example of a model used to determine cardiac arrhythmias from cardiogram data. We would like to leverage the created model to predict whether there is an impending arrhythmia or not by running inferences on the microcontroller, without sending the corresponding sensor data to the cloud. During this process we will show the complete life cycle from training, leveraging Neuton platform, to successfully embedding the model in a microcontroller. In addition, we will show the same process while leveraging TensorFlow. So, in order to train a model on the Neuton platform, you must simply load a CSV file with historical data, in this case various cardiograms, where arrhythmia is noted. The file contains more than 11,000 rows. Amplitudes of contractions of the heart muscle act as features for training the model. We select the appropriate task type and target metric. Neuton provides a number of settings to work with microcontrollers. In this case we choose 8-bit depth support, then we start training. At this point everything else happens automatically. Our manual effort to get to this point is minimal at best, oftentimes less than 2 minutes. At this time the training on the Neuton platform has concluded. Upon completion we have realized the following model characteristics: area under the curve equals 0.96, a model size of 0.7 kilobits, and with the number of coefficients totaling 253. This is an excellent result. Now our model is ready to be embedded into a microcontroller. We begin building a network while leveraging TensorFlow. We first begin by looking for the optimal architecture while also looking to sort out the associated parameters. Here are a list of other potential settings that must be handpicked and validated. This is a long, random and laborious process that does not guarantee finding the optimal structure. We will show the example and results if just one of the many available parameters are selected for the given network architecture. This absolutely cannot be done without special training. In addition, we must spend several hours iterating over these parameters. We begin by initializing the network with one hidden layer, after which we will train and validate the model. We have set aside 20% of the training data as a holdout set for validation. Now that the network is trained and validated, we can see that we have achieved a model accuracy of 0.857 measured with the metric area under the curve. This now becomes our baseline. Let's add one more hidden layer and see if it will improve our results. To see the updated results due to our changes, we must train and validate the model once again. As a result, we can now see that our accuracy has increased significantly, and the measured metric has increased up to 0.96. Let us now change the activation mode of the previously added layer from ReLU to TANH and see what happens. As we know, this is a random and iterative process that occurs when building a model. We now see that our result has decreased in comparison to the previous iteration. Let's discard the activation change from the last step, since ReLU clearly provides better results. Again, taking another step in the iterative and manual process of model building, we will now add another 3 hidden layers, all with the ReLU activation function, and see if this will improve our metrics. We can see that our new score is now 0.956, which is a clear indication that our resulting model is overfit. Let us now once again change the activations of the previously added layers to TANH. In this case we can see that our model got stuck in the local minimum. This time let's change the activation of just one hidden layer from TANH to ReLU. We can see that our model has once again experienced overfitting. After reviewing the previous 2 iterations, we can easily draw the conclusion that our model from 2 steps ago produces the most optimal results. Here is summary of all the differing and necessary steps we took in order to identify the most optimal model. After several hours of iterating over various parameters, we created a model in TensorFlow with similar characteristics as it relates to model accuracy. However, the model size is indeed much larger than the results we would typically see with Neuton. Neuton's model is 47 times smaller than TensorFlow. However, you cannot embed model immediately. We need to reduce it using the TensorFlow Lite converter. We can see that the firmware does not fit into the flash memory of the targeted microcontroller. Therefore, by reducing the list of operations that the interpreter supports, you can reduce its size. In order to accomplish this, we must open the main_functions.cc file and change all ops resolver to micromutable op resolver. Our model requires only 5 operations. Compiling it, we see that the size has decreased. But Neuton's model is still 10 times smaller than TensorFlow Lite model. Now our model is ready to be embedded into a microcontroller. Next, we proceed with opening the archive folder for microcontrollers, which contains all the necessary files, which simply can be transferred to the microcontroller's firmware project. Now to compile the project, we need to press the Build button. After the compilation is complete, we then press the Debug button. The program will then proceed to be loaded into the microcontroller. Click Stop. Everything is ready to run inference in the microcontroller. Next, we take data from a digital cardiograph as input data and transfer it to a microcontroller. If the red light comes on, then an arrhythmia is detected during the reading. Now we see that the green light has turned on, which tells us there is no arrhythmia detected with this particular reading. We see that the light has now turned red once, which tells that everything is once an anomaly within the reading has been identified. We perform similar operations for the TensorFlow Lite model. As we can see, most of the time was spent on manually selecting the neural network architecture, selecting parameters and converting the model, compressing it, and reducing the number of operations. Now let's summarize the results. We see that with the help of Neuton we managed to automatically, just in one iteration, build a model that is 10 times smaller than even TensorFlow Lite. It utilizes 3.5 times less RAM. It demonstrates 2.5 times faster inference time. We also considered other comparable solutions such as Edge Impulse, which has TensorFlow Lite under the hood, however eliminates the usage of an interpreter to decrease memory usage and inference time. Nevertheless, we still experienced lower model accuracy and increased inference time, and still a materially larger model size than Neuton. And most importantly, working with Neuton does not require any special qualifications and implies little human effort to launch similar projects. Neuton's model allows predictions to be made at 2 milliseconds, which is almost 460 times faster than the average heart rate.